Hi. Sure, fairy tales, I presume. We start at 10:45. So yes, there's still several minutes to go. We arrange it as follows. If you have questions, we put them to the chart. If the question is not answered, you just unmute yourself, you speak up, and everything will be fine. All right. Are there any other participants? Don't see anybody, so I will just go to get some coffee. I will be back in. Let's see, is the recording on? It looks like this. Let us see. I have had difficulties with Zoom windows. Anyway, I think I can manage. I think I can manage. And I will I hope this one. We do not have much participants yet. Wonder why is it so? Oh, hi Anam. Anyway, that's still almost 10 minutes. Let's see. What they share actually. Anyway, I'll be back. Hi, good morning. Let us see. Oh, it's time already. Let me show the proper window. Here we have it. So, good morning, ladies and gentlemen. I have not seen you for a long time, for almost a whole semester. You might remember me. I have given you the first lecture of this course. And now I would like to deliver one of the last lectures on the topic which I especially like. I will tell you a tale which is not in Khmelnytsky notes, so it's an extra tale. And yeah, it's a fancy title, Classically Quantum Systems. So why I'm given that, why I like the topic that much that I give it every year, and I guess it's one of my favorite lectures because it ultimately illustrates, at least to me, the total power of theory. Physics is, in fact, made of analogies. And some analogies are simple to grasp and have been figured out at very early days of physics, and perhaps have been also known to many. It's analogy of similar systems like waves. You have the same equations for waves, same approach. It can be waves on a water surface, or it can be electromagnetic waves. The concept is in principle the same. You can do it theoretically, following these analogies. You can also do it experimentally, looking at similarities. There are, however, analogies which you cannot really follow experimentally. And this is one of these analogies, what we are going to see, close similarity, almost one-to-one correspondence between behavior of one-dimensional classical system, which is a subject of statistics, one-dimensional classical system in thermal equilibrium, and Schrödinger equation for a particle. Right, so I pictured the two systems. So, for instance, that's an example of realization of one-dimensional, not the best one, but it looks fancy enough. Realization of one-dimensional classical system subject to statistics. So the very long carbon nanotube with these 17 molecules inside, and they have elliptic shape, and so they can be in two states, either parallel to the nanotube axis or anti-parallel, and that will depend on the neighboring molecules. It can be modeled with a one-dimensional Eisen model, or in continuous fashion with lambda Hamiltonian. And quantum mechanics, how do I picture quantum mechanics? Of course, I use this not very appetizing analogy with a living cat, that cat. Quantum mechanics is really very different from classical mechanics. It uses other way of thinking. It changes all physical concepts we know. However, what we will see in some ways, eventually we will find this equivalence in true ways. What we will see is that there is analogy, almost one-to-one correspondence. So that gives me motivation for this tale. Good. My arrangement with Zoom sessions that all questions go to the chat, and if the question is not answered, you speak up because sometimes I lose chat window. Now I have it. Oh, there's nothing in the chat. May I request you to let me feel your presence? Why don't you type something to the chat? Good morning. Good morning. Good. So at least some of you are not sleeping at this moment. Yeah. So what I will be doing in next several transparencies, I will give very short, condensed overviews of quantum mechanics, as exampled by Schrödinger equation, and statistical mechanics. You're already in advanced stage of your education. There's a chance that it's your last time somebody tells you about this. So please try to follow my outline. And if there are any questions, please ask them because it might be your last chance to get the answer. Good. Schrödinger equation. It is for a wave function. Let this wave function to depend on a certain variable. Let's call this variable x to make it concrete. The wave function evolves in time obeying evolution equation. So here we find operator, here we find Hamiltonian that governs evolution of the wave function. Station solutions of this equation are energy levels. Here I have some. So it is a particle in a potential like this. And what I am given in purple are energy levels, quantized energies. Today I will talk about a single variable x, although everything which I will say also valid for many variables to the same extent. But it's just simpler. Good. So Hamiltonian, we know how to write the Hamiltonian in this case. There will be an operator corresponding to potential energy. And there will be also kinetic energy. Those are abstract operators. To make equation constructive, one needs to choose representation for these operators. We choose X representation, so operator X becomes just a multiplication operator. This is potential energy, which is diagonal in X representation. And so we know the operator of momentum becomes a gradient. So we have a differential equation for evolution of wave function, single variable. Good. We can look at its stationary solution. Everything's clear so far. I guess you have heard about this at least 10 times. Let me talk about statistics. And I always prefer to talk about quantum statistics. Although the system can be quantum classical, and we concentrate on classical statistics. Why do I prefer to make it quantum? Because for quantum system, it is natural to be in a set of states. For classical system, it's less evident. Just the position of a particle is not quantized. It is continuous number, so it would be difficult to sum up over this continuous number. But if you make this particle quantum, just putting it to a large box, you will have quantization of the states. Right. Energies of the states are given, and the system is in semi-equilibrium. This is important. And the right probability to be in a given state, that's all, doesn't come as news to you, is defined by Boltzmann vector. This is proportional to exponent of energy divided by kBT divided by temperature. And the coefficient of proportionality is not known. What is needed to determine this proportionality coefficient? Well, the sum of all probabilities must be 1. So if there's a proportional to exponents, one can figure out what is the normalization coefficient. And this normalization coefficient, which is called, strangely enough, I never understood the origin of this name, don't ask me, which is called partition function. This partition function is eventually an ultimate answer to all possible questions concerning thermodynamics, concerning the system in the thermal state. All answers about equilibrium quantities can be extracted from partition function. Statistical mechanics is a bit unique in this aspect. Let me give examples why partition function contains all possible answers. For instance, free energy is expressed through this partition function. If we look at different quantity in thermodynamics, that's different. If you look at average energy, that can be related to the derivative of the log of partition function with respect to this inverse temperature. I hope you remember, I cannot presume you remember how to prove this formula, starting let's see, starting from this one. This is my question to you. It is important. So if you don't recall how to derive this formula, just let me know. I would be glad to derive it in just a second. This I I'm waiting for your response. No response, so I presume everybody knows how to derive. And also, any average, not only average of the energy, can be extracted as a derivative of partition function with respect to conjugated force. For any variable, pressure, magnetization, one can find the conjugated force. For pressure, this is volume. For magnetization, this is magnetic field. And the partition function will depend on this as a parameter. And extracting it, we can find eventually averages of any quantity, which means that we know everything about the state of the system in thermal equilibrium. Good, that was a short condensed formulation of statistics. No questions? Kind of losing your presence, but what I can do. Just wait for your question. So let us concentrate on a concrete model, which is used in statistical mechanics, which is used frequently and which will be very useful for us today. Let's talk about one-dimensional Eigenvalue model. Right. It's a eventual example of ultimately discretized model. So instead of continuous axis, which I call y, we have just discrete positions, discrete nodes, and we put elementary systems in each node. And this elementary system can only take two possible positions, two spin directions, plus minus. Right. What we can do with these spins, we can apply magnetic field, making one of the positions energetically favorable. And we can set interaction between spins. In that case, it's natural to think about interaction between next neighbors, adjacent nodes in these lectures. All right, let's put some energy related to this interaction, and one can consider partition function at this one-dimensional lectures. Right? In distinction from very many other models of statistical physics, which only look simple, but in fact are tremendously difficult to understand, not to mention to compute. One-dimensional Eisen model remains simple. One can find the partition function of this Eisen model, and that was actually a PhD exercise for easing or icing. Both pronunciations are correct because the guy was German and he moved to United States. So pronunciation has changed. Good. In 1922, this model was given to him in the beginning of PhD, just, as a training exercise. He would do real stuff later, but it turns out that he could not do anything except solving this model. He got PhD, he got his place in history of physics. Everybody knows Ising. Good. Two-dimensionalizing model. Is there anybody of you who have never heard of this model or whatever? That's perhaps is very unlikely, who cannot recall hearing about this model. Doesn't seem to be the case. Right, so as in model, let me talk about different model which is used in statistical mechanics, and there are some reasons to regard it as an ultimate model, a model which can be valid for many systems. Right, we can start, we can try to derive this Landau Hamiltonian for the same as in model. How we do this? So first of all, the variables which we have, and magnetization spin is x now, and space is still y. We can make them continuous, and we can make them continuous by some deformation of discrete models, which is called coarse graining. You perhaps know what is this. Say we have spins defined in a node, and in each node it can take only values plus minus. But if you are talking about a spin of 10 nodes, which is like a still local magnetization, we would have already separation of 0.10. If we are talking about 100 nodes, it will be almost continuous number. So this is called coarse graining. Starting from discrete systems, we just consider bigger pieces of the systems, and we can apply continuous variables to this. Good. Let me figure out what would be the most general free energy corresponding to this system, which has magnetization versus y. First of all, I would like to have some potential, which is a function of local magnetization. So it cares only about values of x at certain y, right? So there's some energy ghosts related to big values of magnetization. There are some energy minimum corresponding to optimal magnetization. Right. So there's some potential. But if we keep only this term, which is very important, of course, but if we keep only it, we will get something bad. Why is it so? Because in KEC we will have a collection of independent thermodynamical systems. The value of x in this point would not know anything about the value of x in a neighboring point, and so on. So the actual profile of x can be very inhomogeneous. To make it homogeneous, and this is a realistic situation, of course, one needs to have a term which adds energy cost for inhomogeneity. This term will be proportional to the gradient of x, right? If x wants to jump, this term assigns energy phi to this. Right. So one can make such a model for any potential u of x. Landau Hamiltonian, it is a certain specification of this u, which is meant to describe second order phase transitions. So it is a function u which contains two terms. It is symmetric with respect to x. And this coefficient in front of the first term is crucial. If this coefficient is positive, the minimum corresponding to this potential, just single minimum, and it is at 0. This is called symmetric phase in the theory of second order phase transition. But if this parameter becomes negative, there will be two minima, and in this case, equivalent minima for this situation. And if the system in one of this minimum is not symmetric anymore, the symmetry has broken. So most of second order transitions are associated with symmetry breaking. And this Hamiltonian, Landau energy describes this symmetry breaking. Fine. I guess I told you everything which is required to start. I don't know to which extent you were exposed to this Hamiltonian. I'm sure that you have seen this picture at least once in your life. I guess it's very important for a physicist. Fine, so let me go on. Let me start with my way. First, I will go from quantum mechanics to classical mechanics. Let us see what I have what I want to do. Quantum particle with a Hamiltonian like this. Potential energy, kinetic energy. I would like to compute partition function of this particle. Right? So it's a summation over all possible states of the system. I just put compact notation. I call this summation trace. Good. What is this? It's a trace of certain quantum operator, which is exponent of this Hamiltonian. Each operator is a sort of matrix, so that has to be matrix as well. In principle, one can do matrix multiplication to determine this. If you know eigenvalues, eigenfunctions of this Hamiltonian, then exponents will be just simple. However, it's not what I want to do. I would like to take this exponent and slice it into smaller pieces. Namely, I would rather consider B as an interval which goes from 0 to this value. And I will separate this interval into small pieces. That will be the length of each piece. And what I want to do now is to make a product of all this smaller exponents corresponding to each slice over here. Okay, mathematically it's trivial exercise and it's not obvious what is the gain for this. We still have exponents. Moreover, instead of single exponent we have a plenty of small exponents. So it looks like we did something wrong or something not very useful. And me, myself also, I could not understand the purpose of it. Why would you slice it in such a way? It was till I was in my true age, and actually we got to a workshop and we have to do sushi rolls. And that was the time I recognized that sushi in natural state is just very long roll, about meter long roll, which is impossible to eat, impossible to swallow. That's why Japanese slice this roll into very small pieces, and that becomes edible. Again, it's the same concept here. It is easy to operate with each small piece separately and then collect everything into a single picture. So we will concentrate on this small operator, slice operator. Let me recall that this is a matrix. A matrix which has two indices. In this case, indices correspond to variable x. Roots, right, already at this stage, we can see some Schrödinger equation emerging. Which is not surprising because we are talking about quantum mechanical system, but it's not precise as a Schrödinger equation. First of all, what I'd like to do, I would like a wave function to evolve with application of the slice operator. So I define wave function at one slice. To proceed on the next slice, one has to multiply it with operator temperature. And so on, so on, so on. And that looks like evolution. That looks like evolution of a wave function, but not in time, but rather in this coordinate. Let's name it. It is imaginary time. So one can use the slice operator to consider to make a wave function to evolve an imaginary time. So this is a difference between the equation I have and real Schrödinger equation. Imaginary unit is absent here. Why? Because time is imaginary. Good. What did I use in order to come to this? What did I use in order to reduce it to this form? I expanded exponent in Taylor series at small intervals, right? Then I put it here, and I come to this equation. Is this obvious to everybody? The steps. I can concentrate on the steps if you wish. Good. Taylor expansion, and from discrete equation on discrete imaginary time, we go to continuous equation for continuous imaginary time. We expand in the exponent meanwhile. Fine. Then let me make next step. Let us make use of the slicing finally. And the use will be rather unusual. First of all, right, I had operator multiplication here. Combining the slices together. I'd like to remind you that operator multiplication is just integration. It's extra integration. So anytime I have two operators next to each other, I can write this product as an extra integration. With this, look, what do I have for a partition function? I have integration over very many variables. Each slice delivers me a variable to integrate upon. Or in other words, each moment of imaginary time gives me a variable to integrate upon. Right? So that's very multidimensional integral. And let me transform this further using the fact that slices are tiny. I can easily swallow it. I can operate with them. So there's approximate commutation for the small slides. To check it, you just expand it in delta t. You see how good it is. So let me separate the slice operator onto contributions of potential energy, which is diagonal in X. And let me have contribution coming from kinetic energy, P squared over M. I want to compute it as a function of X and X prime. And what can I do? I can recall that it's eventually a conveniently diagonal operator in momentum representation. And right, then I go to coordinate representation. And that's what I have for this slice operator. You recognize Gaussian function, and this Gaussian function kind of keeps neighboring axes close together. So it makes neighboring axes at neighboring slides to be close together. Good. Let's now put this and this, both are exponential functions. Let's put it here. It's fine that we have exponential functions because if we multiply exponents, we actually got exponent over fun. Right? That's what we get. And also, I want at this stage to smooth distribution of X. So there are no fluctuations from node to node, not at all. I just make it continuous. In this case, I can change it, differences of axes at neighboring points into derivatives. Good. And let me take the limit of very, very tiny slices. Then what I obtained for partition function of a quantum object is a path integral representation. So, collection of all axes at all time moments, it is a path. Here is an example of it. The passes must be closed. Here's the value of X at 0 and at beta must be the same. Why is it so? Because that is a trace. So that is trace. Initial and final indices of this matrix must be the same. So its summation over such trajectories passes, and each pass is taken with a weight. Weight is exponential, and look how does it look like. It contains energy term, and it contains gradient term. So let me make several steps back. We are here. We are in statistical mechanics. So X can be regarded as a classical variable, magnetization, and T can be regarded as a space variable of some one-dimensional statistical field. All right, let's make a break at this point. Let's make a big break till 11:45. Let's see. Good, good, good. We still have 10 minutes. Let's see. Wanted to send a couple of emails. Okay. Very good. So let us see. What did I stop? Still a couple of minutes.
Can I have a question in the meantime?
Yes.
Can you explain what's the meaning of the delta function in the
Sorry, I have to do something with my volume. Just a sec. Yes, please repeat the question.
Could you explain what's the meaning of the delta function in the first product in the partition function in the top of the slide that you're showing now? It was already present before. I'm still not.
You mean
sure.
this?
Yes.
Okay. To understand this, we have to go to very beginning to the presentation of Z as trace. If I rewrite this trace in a matrix form, I would do integration over X of a matrix in the same indices. Okay. Right.
I think I understand already.
Sure. It means that the final, initial and final values of X must be the same.
Okay, I understand. And one more question. When you slice the beta operator, you called it imaginary time, but in the end, beta is temperature. So why didn't we use the concept of temperature here at all? Is that somehow physically relevant?
It is inverse temperature.
Yes, I agree, but
Yep.
But still, they share the same properties, sort of like temperature cannot be negative. And can I somehow physically relate this, or is that not relevant at all?
Physically relate what and what?
I'm just still wondering why we moved to the concept of time instead of just staying with temperature. Maybe for understanding it would be still better to keep it as temperature or not.
We use time because we ourselves live in time. Concept of evolution is natural for us. That's why we tend to call everything which evolves time.
Okay.
Right? Here also, it's not the process which goes in physical time, but value of this matrix evolves. Value of X evolves in some variable. So this variable is just called time. More whatever confusion or inspiration you have if you look at this Schrödinger equation, which coincides with a common Schrödinger equation on imaginary unit.
So you are saying that the departing from the concept of temperature and calling it imaginary time made it possible for us to somehow arrive at this whole idea of going towards Schrödinger equation.
Right. It kind of gives us an opportunity to see analogies.
Yes. Okay.
I could call
understand.
it somewhat different, but then the analogy would be difficult to see. Very good. But it's time to me to go with the course. Let's see what we have achieved at this moment. We manage to represent the partition function of a quantum system in classical terms. In perhaps I formulate a control question. Wonder how they go about this. We managed to formulate it in completely classical terms. Namely, we reduce it to passes, which can be seen as configurations of classical one-dimensional field, like magnetization, which depends on coordinates, right? And well, each magnetization, each configuration corresponds to certain free energy. So it is a description in terms of classical statistics. That's what we achieve. So we went for quantum, from quantum to classical. Now we are going from classical to quantum, but here I have my tricky control question. If whatever you exposed to some quantum computing course, whatever somebody tells you about quantum computing, they tell you that in fact quantum states are much more elaborated than classical. They contain much more information because of the superposition of wave functions. It's all that. And whatever, is it hype or not, they are right. Nevertheless, I managed to do this. I managed to describe quantum system solely in terms of classical mechanics. Must be something wrong with this. What is wrong? What is the, in more exact terms, what is the assumption which allowed me to do so? This is question to you. That's since there are not so many assumptions done. The assumption is also rather at surface. You only need to recall it. So, who can answer? I don't hear too much enthusiasm. Let me spell it out, and this is somehow important. We have not considered a general quantum system. We have considered a quantum system in thermal equilibrium. And there, in equilibrium, we don't have much information. As I said, everything is incorporated into partition function. Thermal state is rather unique state. It is still quantum, but a thermal state doesn't have so many peculiarities which are discussed in the field of quantum computing. All right, that's rather important piece of information. Let's go further. Let's go in opposite way. Let's start with classical system and let us see quantum mechanics in it. Right? To this end, I will take one-dimensional lattice model, and it is convenient to me to do it in a bit more general fashion that the eyes indeed. I still have nodes arranged in a lattice, but the variable which is defined at node doesn't take only two values. It can take any set of values, can be discrete, continuous, the sum variable are x. All right? Good. With this, I still can define a kind of generalized lattice model. I can define the energy per node, which will depend on this variable. That will give me Boltzmann weight. Don't forget that it's Boltzmann weight. Okay, BT associated with this. I can also think of energy per bound, which depends on x onto neighboring nodes. That would also correspond to some weight. Oh, small taper here. Good. Let me write down partition function in these variables. Here it is. So what I do, I have to integrate sum over many axes. And I have a product of Boltzmann weights for each node and for each bond. Look, it's first bond, first, the second node, then there will be pairs of products like this for all nodes. All right. It looks already similar to what we have done recently when we have been talking about slices, and we have separated each slice into two parts. But anyway, we will see it in more details a little bit later. Good. Then how to solve this partition function, actually. How to deal with that. Usually one does the following. So there's this awful number of integration to make. Suppose we've made a part of this. Suppose we made till all integrations till node I. Right. What would be the answer? The answer will be a function of this of the variable on the next node. Right. It cannot depend on previous configurations because we have integrated over them. It can only depend on the variable which is connected by bond to the last node we integrate upon. Good. In this case, we obtained a function like this. Let's make yet another step. Let's make next integration. That's what we will have. So the operator which connect these functions. They're not wave functions. I use psi for that, but they're not wave functions, absolutely. Some functions of x. Right? They're just related by this equation. So again, it's a discrete evolution, and it's obtained with this integral kernels corresponding to energy per bond, corresponding to energy per node. Good. How to proceed further? Solving this partition, or solving this partition function. One looks at Eigenvalue Equation. This operator, as any operator, has eigenvalues, and this is equation for this. And partition function is given by the eigenvalues of this operator. Right? It is simplest way to prove it is to impose periodic boundary condition on this system, just to make identical first node and last node. Right, in this case, psi over certain number of steps must become itself, right? And that evolves eigenfunction to the power of n, sorry, eigenvalue to the power of n. So that's what we have for periodic boundary conditions. If one can go to the limit of big N to the limit of long chain, and in this case, the eigenvalues compete, the highest actually wins the whole game. The highest eigenvalue grows faster with increasing N than all others. So the partition function will be given by the highest eigenvalue. Right, so that's what we wrote. And in principle, it's all about classical system. It doesn't apply any quantum mechanical reasoning. But let me try to draw analogies with quantum system. Good. So for finite, for quantum system with certain energies, the partition function will be like this. And this is analogy with this one. Right. So temperature of quantum system plays the same role as a length in classical system. Right. Small t limits, partition function is given by the lowest energy state. Everything is in the ground state. That corresponds to this limit of big length. Right. And if we can make continuous limits, if we, by some coarse graining procedure, if we can make y which is defined at nodes. If you can make it continuous coordinates, then let us see. This just becomes gradient term. This becomes potential. So this is analogy with kinetic energy of a particle and the potential energy is analogous to potential energy. Fine. Let me make two practical examples. What I told to you were rather general derivations, general pieces of information. Let us see how these analogies work, how they are useful for concrete models. And I take two examples from classical system to quantum and from quantum system to classical. So I start with an Eisen model in external field and again, absolutely classical. And I will try to see quantum features in this model. Good. To do this, we need to solve this Eisen model. And I find it convenient to do a little bit of symmetrization, which will help me to compute the eigen values of this equation. All right, so what I had a product of two operators like this. That was eigenvalue equation. I can symmetrize. The point is that it's not Hermitian operator. I can make it Hermitian if I symmetrize it. So I kind of cut this double into two parts and put one part on the left and another part on the right. With respect to eigenvalues, it will be equivalent procedure. Good. Let us figure out what does it mean for Eisen model. First of all, the magnetization or x coordinate is discrete. It can take only two values, and that's how the factors look like. The energies corresponding to magnetic field and to interaction between nearest neighbors. So because x can only take two values, well, it would be like a qubit. We'll have 2 by 2 matrix to play with, eventually to diagonalize. Right? Elements of this matrices can be computed taking different sigmas plus minus 1. So here we have it. Those are eigenvalues. One can also find eigenfunctions. So we kind of solve Eisen model by quantum mechanical way by computing an eigenvalue. But the analogies can go on and on. To make it more explicit, let me, without much of detailed calculations, let me sketch the averages. Sorry, I have to say what I'm doing. Some formulas which I put here require some lengthy derivations. I don't want to do this, so I just let these formulas. The main thing to look at is analogy with quantum mechanics. Good. So let me do something more interesting with one-dimensional model in hand. Let me average some function. So take some mechanical average of some function at one particular node. Good. It's statistical mechanics, but the answer which one gets for this average is pretty much quantum mechanical. It's precisely like average of operator between two psi functions. This wave function corresponds to ground state. Looks natural. The system is in ground state because you can see the very long system. It says corresponds to the limit of very low temperatures in quantum systems. The system is in ground state, so this is average in ground state. Let us now consider correlations. So we have nodes, and we consider average, which involves x at this node and at this node. Right? And when we derive this average, it contains two quantum elements. First of all, this happens here. So till this node, we have kind of ground state, wave function phi node. Here, in this set of nodes, the system kind of in a high state. I have summation over states. And I have matrix elements which might be associated with the transitions between these states. So, full analogy between quantum mechanics, which is not there, and thermodynamics of Eisen system. Good. What I would also like to define for future use from Eisen model is the concept of correlation lengths. So all these things correlate only at a finite length. If you consider it at very distant nodes, the variables at these nodes should not depend on each other. So, and how to compute estimate this correlation length? One needs that if there's distance between the nodes, that's how much one should pay for this, right? So correlation length must be kind of log since this is kind of length divided by correlation length. Length is proportional to n, so correlation length is like this. So it's defined by the first excited state. Right. Then in Eigen model, we can look at correlations of magnetizations. We can find two states, so we can find correlation length, and we can get some limits for this correlation length. First of all, let me consider the case without magnetic field. Then at low temperatures, which correspond to small k, in the absence of magnetic field, correlation length is exponentially long. Why it is the case? If one looks at the profile of this magnetization as a function of y, the spins would like to adjust each other. They would like to be together. So magnetization would be like this. But then it can jump to precisely opposite vector. So in fact, configurations are connected to these domains. And the correlation length in this case is the domain length. And if temperature is low, the domain walls, which cause energy, they appear very rarely exponentially with a Boltzmann factor, which is exponential in the inverse temperature. So at low temperature, the correlation length will become bigger. But if you apply magnetic field, the situation will change because one type of domains will prevail domains of other type, and that will restrict correlation length by. Fine. Let me get to complementary analogy. Let me start with a quantum system, and let me understand this quantum system in terms of one-dimensional statistical. Good. What kind of quantum system I can envisage? Well, it's of course qubits. So we will talk about qubit physics. But to make it more consistent with the material which we have already discussed, let me make a little bit concrete qubit. So to make my qubit, I will start with a two-level potential. Right, two-level potential, which has two potential wells at plus and minus 1. I would like also add some asymmetry to this potential wells. This asymmetry is called epsilon. Good. Next, I assume that the barrier is sufficiently strong. So the tunneling between the wells for the states of this energy is weak. Then wave functions approximately localized in each well. Each well I can approximate with a kind of parabola. And then it is reduced to an oscillator. So bottom levels are levels of an oscillator. And now I would like to concentrate on the lowermost pair of levels. Now I would like to recall quantum tunneling, otherwise the problem would be too primitive. I would like to recall quantum tunneling with an amplitude delta. So delta comes as a non-diagonal matrix element to the Hamiltonian of this qubit. All right, we can solve the problem about tunneling through this barrier. So this is exponential separation of this delta. Fine. Okay. I end up with two-dimensional Hamiltonian. Which one can solve? Get energies of the qubits and understand that the qubit is not in a certain state, it is in a certain well if the wells are precisely and aligned. Qubit is delocalized between these two wells. But well, if one increases this energy splitting, then the wave functions are such that they are localized in two wells of the potential. Good, it was completely quantum consideration of this problem about the qubit, which I guess mostly known to you. If it's not, it's perhaps your last chance to ask a question about qubits as it emerges from double well potential. Fine, no questions. Let me translate it in 2D. Right? So I have this potential over here because I can immediately utilize it, and I can write energy for corresponding Landau Hamilton. This is what it. So X now is a magnetization which depends on spatial coordinate y, right? And I have different classical configurations. Let me understand what does a qubit maps into this picture. Right, two wells which we have in this potential are two degenerate magnetizations, as we just discussed, Dimensionalizing Model. There are two equivalent directions, opposite directions of magnetizations, which have the same energy if magnetic field is 0. Right. There can be quantum tunneling between these wells. In classical language, it corresponds to domain wall, which separates these two regions. So the jump doesn't occur immediately; it occurs as a certain thickness. Right. Quantum amplitude of quantum tunneling, which is exponentially suppressed. It comes as exponentially small Boltzmann rate at low temperatures. The domain wall of this kind, it has finite energy, and if temperature is low, then the probability to find such a wall becomes exponentially small. Right. What is the meaning of parameter epsilon? Here, in classical picture, it leaves the degeneracy between two magnetizations, so it works like magnetic field. From expression for quantum energies, one can eventually solve the quantum problem from our expression, which has obtained by declinization of the qubit. Right, so this is free energy as a function of two parameters, epsilon, magnetic field, and delta, which contains these exponents corresponding to quantum tunneling. One can also compute magnetization, just by differentiating this with respect to epsilon, which shows how, well, basically what does it do? It shows relative probability to be in energetically favorable state or energetically unfavorable states. So domains becomes shorter, and okay, one can also elaborate on correlation lengths given by this expression and related to two limits without with magnetic field and without magnetic field. Good. That completes my story. Let me, since the story was long, let me get to the beginning. There are analogies in theoretical physics which we can use, which we can make practical, which go beyond usual level of analogies. Here we draw analogy between classical one-dimensional systems and zero-dimensional quantum systems. Generally, it can be analogy between quantum system with n dimensions, and the classical system with dimensions n plus 1. It also works for multiple dimensions for both systems. And this analogy is something which is frequently used in field theory and statistical mechanics. In fact, it's a commonplace for many courses of theoretical physics. But I find it an interesting manifestation of true power of theoretical physics. Any questions to conclude? We still have time, 1 minute. So since you did not ask any questions, let me ask the questions as usual.
Can I have a question? I sent it in the chat, but I'll just say it. In the last slide, you mentioned the thickness and that it's equal proportional to inverse omega. You didn't elaborate on that. What is the omega here? What is the origin of it?
Here it is. So omega just a convenient notation for oscillator frequency. This frequency gives us some time scale associated with the motion in the valve. And when you go to coordinate, coordinate is time now. So the width of the domain wall is associated with this time scale.
Yes, I understand now. Okay, thank you.
Good. Then the time is up. The question which I wanted to ask is, how do you like this course? But I guess the answer is rather obvious just from the fact that you're present here. So thank you very much. I appreciate your attendance. Have a good day. If there are any questions, comments about my lectures, about lectures of others, please write to me. I am responsible for this course. With this, I want to say bye to you.
Thank
See you later.
Thank you. Thank you for the lectures, and goodbye.
Thank you.